That what hit?
Really concerning for whoever's throwing.
Yay, boobies!
I'll redo it. Redo it again.
Hello, this is Batish.
Takase,
Piotrowiak,
and Alex Bollwitt.
And today we're going to be breaking down and analyzing the thrilling and chilling sport of curling.
Yes, curling.
The clip we'll be analyzing today comes from the Home Players Championship in Grand Prairie, Alberta, from earlier this year.
And as first, let's point out that this is an example of horizontal motion, which is what we're going to be talking about. We're not doing projectile motion or vertical motion, and we know that it's not neither because the rock stays on the ground. To begin with, we're going to talk about Newton's first law, and if we can run the video, we can first say or talk about equilibrium. Yeah, and equilibrium is when the net force on an object is zero. In this case, and if you look at the free body diagram here, we have the force of gravity down, the normal force up, the force of friction, and the force of whatever APP is, which you can say is applied force. And as we know, and we look at the video, that the rock is not moving. She's not touching it, or she is touching it, but the rock is not moving. And in this case, the force of gravity is also equal to the normal force, and because there's no applied force, there is no friction to keep it back. And there's two cases where the net force would equal zero, and that we would achieve equilibrium. Is when the object is in constant velocity, or when it's at rest.
Which is constant velocity.
Which is technically constant velocity.
Which is also Newton's first law.
And Newton's first law, which is the law of inertia, say that every object that is in motion or at rest would stay in motion or at rest unless acted upon by an outside force. And
now if you'll roll the clip. This applies here because she starts at rest and it's at rest. Now when she starts applying the force, she's moving forward and the stone is moving forward. And they both keep traveling forward until an outside force, which, and if you'll see here, is the next stone is applied. That stops that rock. And then the further stones hit also move because they want to keep moving because of the force applied them in that direction.
yes, you can also, if you go back to the beginning, point out that when she stops, the stone keeps moving. As we'll see here soon.
Well, she doesn't stop. She lets go of the rock.
She lets go. And she slows herself down while keeping the stone moving forward.
So she's staying in motion at first.
Yeah, at first we know she's slowing down because of friction or the little
Friction and
stick
transfer
thingy.
of momentum.
Let's wonder for this section.
Alright, for Newton's second law of motion, which is force equals mass times acceleration, which we should all know from previous chapters, that is also shown in curling. And I will start the video. Now, here. The force equals mass times acceleration. The force is coming from this lady, woman, girl, whoever. The mass is the stone that she's pushing. And by applying force to a mass, she will accelerate the stone, and that's how it moves forward and runs into the other blocks. Now, it goes forward, and right after she releases it, there's no force, any more force forward being applied, but there is a force backwards, which is friction. In an ideal frictionless situation, since there are no forces acting, the stone would move on forever, but in this case, the friction will slow it down eventually. Now, she did throw it forward, and it will not change motion unless another force, boom, right there, is applied on it. And the hitting of that stone to the other stone heavily decelerates it, and if you look closely, it also, because of the angle that it hit, and they're both circles, it deflected a little bit and it went towards the side.
this part of the video is on the conservation of momentum. What is momentum? Momentum is the product of the mass and velocity of an object. And the conservation of momentum is that the total amount of momentum at the beginning of an event and at the end of the event will be the same. And in this event, the curling rock will start out with 0 momentum because it has 0 velocity. And also at the end of the event, it will also have 0 momentum because it will also be stationary, having 0 velocity. Now let's watch as the changing of momentum throughout the event happens. First, you have the chick. The chick is going to apply a force to the block. The block will apply a force to her, and she will in turn do work on the curling rock. And since she does work, she's transferring the force and also momentum because she is giving it a force, meaning it will accelerate, and it will also have velocity, meaning it will have momentum. Now she pushes off, she applies the force, and the curling rock now has momentum because it has speed. Now as the curling rock travels along and due to friction, it will lose velocity, it will also lose some momentum. Now here it hits the other curling rock, therefore transferring its momentum through a force, and since it does work, the other curling rock also gains some momentum because it gains some velocity. Now this curling rock will hit the other curling rocks. Now this will be a complete mix of rocks hitting other rocks, but each time another rock hits another stationary rock, it's applying a force, giving it acceleration, therefore giving it velocity, therefore giving it momentum. Now at the end, most of the blocks are moving, but if we look back, the first block, which is at the top part of your screen, which I will identify, it's not moving anymore. It is stationary, having no momentum. Therefore, being that it has no momentum just like at the beginning, conserving momentum. Now these blocks go all over the place, and soon they will decelerate due to friction till having 0. But in that time where they are moving, they have momentum due from the changing of one object which had momentum, applying a force to the other stationary object, giving it velocity, giving it momentum.
Conservation of energy. Alright, so in our scenario here, we start out with a lot of potential energy. Now, as the woman does work on the rock, this potential energy becomes kinetic energy. Now, when it first starts going, the kinetic energy is really high, and the potential energy is practically 0. As the rock keeps going, the kinetic energy decreases over time, and the potential energy increases. The potential energy plus the kinetic energy will always equal the same value throughout the transfer process. This is the conservation of energy. Now, as the rock keeps going, this energy will transfer to the other objects as the rock collides, and then it does work on the other rocks, and this energy will split between the other rocks, and they'll have kinetic energy, which will decrease until they stop, and all the energy will be potential.
Alright, for Newton's third law, we have the definition as every action has an equal and opposite reaction. Through the same principle, we can tell that a force that is applied has also a force on itself in a negative direction. This is more intuitively can be seen easier in the beginning of the video when the lady pushes on the ramp, or whatever this thing is. As she pushes on it, she applies a force to it, and because of Newton's third law, it applies a force back on her, allowing her to move forward. As you can see. What we also know about Newton's third law is that it's in the opposite direction. As you saw, she applied it backwards, therefore the ramp applied it to her in the opposite direction, which is her forward. And that is Newton's third law.